Hello and welcome to this training for the Copernicus Marine Service focused on the Northwest European Shelf. My name is Alexandre, I'm from Noveltis, and today I will show you how to manipulate the CMEMS products in a Python framework. More precisely, today's training will be focused on net primary production in the Northwest European Shelf. As a reminder, net primary production can be defined as the accumulation rate of biomass in the water, which makes it an essential environmental parameter because it is what sustains marine life, providing food for fish, indirectly for bigger fish, and eventually for humans, as it sustains the amount of seafood that can be retrieved from the water, which is why such primary production is a crucial parameter to monitor. It is all the more important because of global warming, net primary production is expected to decrease in this region, as you can see on this graph from the IPCC. So in this notebook, we will look at net primary production over the last 20 years and see if there are already trends that are noticeable in the data in this region. And if so, we'll try to study if this trend can be correlated to other environmental parameters such as temperature, acidity, or nutrients. So we will be working in this notebook with Python, as you know. So in this section, I will show you what Python environment we're using, and more importantly, what modules we will be importing to manipulate our data. If you are familiar with Python, you probably already know some of them. So we'll be using NumPy, which is a fundamental package for manipulating arrays in Python. We will use xarray to open the CMEMS products and store them. It's a very convenient data format. Matplotlib will be used to plot graphs, and Cartopy will be used to plot maps along with Matplotlib. We'll be importing datetime to manipulate dates, because we'll be, of course, looking at time series of data. And finally, we will use some functions of the SciPy module, which is a very vast module. It has very wide collections of algorithms. And in that case, we'll only be using a few functions to compute statistics, so linear regressions and correlations. So in this cell, we're importing our required libraries. It takes a few seconds. Oh, it's done. And now that our environment is set up, let's have a look at our data. So this is the main project we're going to use in this training. So the product we're using is an output from a numerical model, which has also a few observations assimilated to it. So it's called the Atlantic European Northwest Shelf Ocean Biogeochemistry Reanalysis dataset. So it has a lot of variables besides net primary production, but in this particular case we'll be studying NPP. So here are the key information that you need to know about the product. Its spatial resolution. We'll be working with monthly means of net primary production. It covers, it has a temporal coverage from 1993 to 2022. However, in this study, we'll only use data from 2000 to the end of 2019, so 20 years of data. And it has 3 depth levels, and you'll see that in this notebook we'll only look at data at the surface level. And for any more information, of course, you can always refer to the product's documentation and to the product user manual and quality information documents. You'll have all the information you need in there. Okay, so let's get started. Of course, as I forgot to mention, so let's get started and open the product. So before anything, you see that in this directory, the NPP data is already available. If you want to download the product by yourself, you can refer to the beginner notebook, which explains all the different methods to download data. So we'll use xarray to open the dataset. Let's see what happens. So here you can see what the dataset contains. As said before, there are different depth levels, so only 2 here it seems. You can see the latitude attribute, the longitude attribute, and the different dates of where we have data, and a lot of other attributes to the variable, which we don't need to go into here. So as we can see, this is our variable of interest, NPP, net primary production. So first, let's see what our data looks like on a single date. So this will be just a basic plotting that you should have already seen in the beginner notebook. So it should be easy. So here I've decided to plot the NPP on June 2015. I've saved here the variable, which I'm selecting here. I'm selecting the date with this command. And with this command, I choose the surface level with depth equal to 0. And here are all the lines to help plot the map. So here is our data plot on the June 2015. So this is the net primary production in milligram per met cube per cubic meters per day. As we can see, net primary production is very concentrated on the coasts and has higher values also in shelf seas. At least those values are a lot higher than in open ocean. So it is probably in those sort of area that we're going to focus our attention. Okay, so at this point, what I want to know is, are there in this region any areas where net primary production is significantly increasing or decreasing? In order to see that, we are going to compute trends all over this map. So we're going to see over the last 2 decades, from 2000 to 2019, if there are decreasing or increasing trends. So that's what we are going to calculate right now. Okay, so in order to do this, as a reminder, we have monthly values of NPP. We don't need to have such a precise temporal resolution to compute trends over 2 decades. So first we are going to resample our data to have yearly means instead of monthly means. So this is done with this line. We're still selecting only surface level NPP and grouping them by year and averaging the values over time. So in order to compute the trends, we are going to perform a linear resolution on each pixel of the data. So we are just storing the values here, storing the dates here, and computing the linear regression thanks to this function. So it's a polynomial fit from the NumPy library of degree 1, because it's a linear regression. And let's see what happens once we've computed those trends. So this is our trends dataset that we're going to plot as a map in the next cell. So the process of plotting is fairly similar to the one you've seen before, only we're plotting different data. So this map shows the trend followed by NPP for each pixel of the region in the last 20 years. So here the unit will be in milligram per cubic meters per day per year. And as you can see, there are areas where the NPP is decreasing a lot, especially around coasts. And in this region, we can say there is a large patch of decreasing NPP. And this is the area we're going to focus on during the rest of the training. Okay, so this area is called the German Bight. And so what we've seen is that there is a very decreasing trend of NPP. So now we are going to look at other variables and see if they follow the same trend or if they can be correlated to the NPP decrease that we have just seen. So the first thing to do is to crop our dataset or subset it just to have only this area in our data. So we'll be delimiting our square with its minimum latitude, maximum latitude, minimum longitude, and maximum longitude. So let's just execute this cell to have those variables active, and let's just check if our square is properly defined. So this is the square we've just defined, and it perfectly captures the area we want to study. So now that we have selected our subset in the data, we'll be spatially averaging it to have a time series of the average NPP in this area. So as a reminder, here this is a line where we subset our dataset spatially, so where we cut according to the square we've delimited. And here we're performing the spatial mean to have monthly and yearly values of NPP over this area. So let's plot the time series and see what we get. Okay. So this is the evolution of net primary production over the German Bight. In blue are the monthly values, and in green are the yearly means. So of course the two curves follow the same trend, and we can see, especially in the last 12 years, that there is indeed a slowly decreasing trend, which is fairly visible here with the maximum monthly values decreasing over time. So indeed we can see a decline of NPP, especially in the last 12 years. So now we'll be looking at other parameters to see if those parameters follow a similar pattern or not. So we'll be looking at other parameters, which means we'll have to use other datasets. So I'll present them to you very briefly. So we'll be looking at pH, water acidity. This variable will come from the same product as the products where we had NPP. So it will be the ocean biogeochemistry reanalysis. Same thing will go for the two nutrients we've chosen to study, nitrates and phosphates. So if you want to know more, of course, you can refer to the same user manual as before, as we've seen in section 2.2. We'll be also looking at sea surface temperature, SST. This product will come from reprocessed satellite observation, so it won't be a numerical model output. And finally, we'll also look at salinity. This salinity will be taken from in situ measurements, measurements made by a fixed buoy in the German Bight. I'll show you its location later on when we get to this section. The point here is to manipulate different kinds of products, and you'll see that each product requires its own pre-processing. So let's see what happens when we look at water pH. So water pH is a possible driver for this decrease in net primary production, because high acidity can cause stress on the marine biodiversity, and we know that because of the increase of CO2 concentration in the atmosphere, the open ocean absorbs a lot more CO2 than before, and therefore its pH is slowly decreasing, and this has an impact on marine wildlife. So it's relevant to look at water pH and try to correlate it to the decrease in NPP. So same here, we've already downloaded the products necessary for this training. So let's open it. Okay, we can see that it has the same structure as the NPP dataset because it comes from the same product. We still have two depth levels. So those are also monthly values. We have our pH, and the attributes are the same as in the NPP dataset. So now we'll perform the same steps as we've performed with NPP. So we'll subset it to our region of interest, the German Bight. Then we'll perform the spatial mean over the area to compute the monthly and yearly time series. And finally, we will plot the data. Okay, so we can see that pH in this area is also steadily decreasing. It doesn't follow exactly the same pattern as NPP. If you can remember, NPP had a sort of steady, slightly increasing at the very beginning of the 21st century, and then started really decreasing after 2008. Here is decreasing during the whole period. So yes, it's we'll see afterwards when we calculate quantitatively the correlation, but the pattern here seems a little bit different. Next, still from the same dataset, we'll now look at the nutrient concentrations. So as now you are quite familiar with the processing methods, I'll go a little bit faster on this section. So we're opening the data from phosphate and nitrate. Here, for an example, I'm just displaying the nitrate dataset. So yes, it's still the same structure as before with the same attributes, also the two depth levels. And just as before, we will subset the dataset, perform a spatial mean to have the yearly and monthly time series, and see what comes out. And just as usual, selecting surface level, selecting our area of interest, resampling by year, and plotting. Okay, so now we have our plot of nitrate and phosphate concentration over the German Bight expressed in millimole per cubic meter. So we can see that in this case, the two curves follow a slightly similar pattern as the one followed by NPP, with slightly increasing in the beginning of the century, and then after 2008 or so, a noticeable decrease. So when we calculate the correlations later on, we might have some good correlations here, so we'll see later. But yeah, this is a definite potential driver of the NPP decrease. Now, of course, we've said that global warming was a probable was expected to cause the decrease in the next decades of NPP. So it makes sense to look at the sea surface temperature at their evolution the last 2 decades to see if there is a correlation with NPP. So in this case, the processing part will be a little bit different because we are using a different product, as you can recall. We have satellite reprocessed observation to make our SST products, and this product has a temporal resolution of daily values, which means the data takes a lot more space than our previous datasets. So the data has been split in 4 files of 5 years each. So I can show you where they are stored. Daily SST. We have 4 files here. And the first step of the preprocessing will be to open the 4 files and merge them all together in order to work with only one file. So in this cell, we're just listing all the files that we have in our folder. So there are indeed the 4 files we are studying. Here I've written a little function to pre-process the SST values. So in those products, the values are expressed in degree Kelvin, and for readability and better understanding of what we are studying, we want to convert those Kelvin to degrees Celsius. So that's what this function is about, and it changes just it just applies an offset to the data. So let's open our files, and we've opened them thanks to the open mf dataset function. So it allows us, it's an X-array function that allows us to open multiple files at once. And when I display them, you can see that here the data is still split into chunks. So we have 4 chunks of data. We still don't want that to work. We need to have, just like before, just one chunk of data. So in order to have that, we'll just export this data into a single file and reopen it, so that we show we are working with one full file only. So this is where we want our new file to be stored. So I've named it 2019 because it spans the whole period. It will be in this folder. I'm going to delete it just to show you it will come back. So this process, of course, because the file is very big, it will take a few minutes. So I'm just going to pause the video and come back with you when it's finished. Okay, after now a short pause has happened, and the cell has finished executing. So the file should be here. If you can't see it, just try to refresh the page, and nothing happens. Why is that? So after a few minutes, the cell should have finished executing, and the dataset should appear in the full directory. If it doesn't appear, just try refreshing the page, and you should find your file. So now let's reopen this file, which here we are calling the dataset 20 years, and see what happens. So we do have a file, and here we can see that the values are not separated into chunks. At least they should not be. Another thing that is different from the previous datasets, which came from the ocean biogeochemistry reanalysis, is that the attributes of latitude and longitude are here called lat and lon. So this is an important parameter, an important thing to notice, because afterwards, when subsetting the datasets, when selecting latitude and longitude, you need to not forget to call them lat and long instead of latitude and longitude as we did before. So now that we have a dataset on the 20 years period, we'll do exactly the same thing as we did before, which means subsetting it to the area of interest and computing monthly and yearly sea surface temperature values. So for temperature, we're going to do an additional thing, which will be splitting the years by seasons to see if there are special correlation for summer months, autumn months, winter months, or spring months. So our sampling method is the following. For winter, we are selecting only January, February, and March, so month number 1, 2, and 3. For summer, for spring, we're only selecting April, May, and June, and so on until October, November, December for autumn. And of course, we're still looking at SST values over the whole year. So let's do this computation, and let's plot all the time series that we have computed. So as a reminder, yearly values and yearly values split by seasons. So yes, there are a little more things to plot, so the cell is a little bigger, but we are essentially repeating things that we have already seen before. And of course, it takes a little more time. Okay. So this is just an illustration to check that we are plotting the right thing in the right area. So this is the area we've selected with a sea surface temperature on the 7th of July 2019. I've only chosen this date arbitrary, so you can really choose any date you want to plot this map. So the temperature is shown in degrees Celsius. And here is the yearly SST over time. So here for whole years. Here is the overtime, but only on winter months, and so on. So yes, looking at the pattern, we can't really see anything similar to the NPP, at least from mere observation. We'll try to have a more precise calculation of the correlation afterwards, but this doesn't look very promising. We'll see afterwards. Finally, let's have a look at salinity. So high salinity can cause osmotic stress and potentially negatively impact net primary production. So there have been inverse correlations found between high salinity and NPP. So in this section, we'll try to look at in situ dataset taken from a fixed mooring that's located here. So right in the middle of the German Bight. And we have accessed this data through the CMEMS In Situ Thematic Assembly Center portal, which you can also freely access with your CMEMS account. You can find a great number of physical parameters and in a vast number of locations. So after this training, you can always go on this portal and find some data to play with. But in situ measurements are not the same as numerical models outputs or even reprocessed satellite observation. So you will see that it requires its own pre-processing steps, which is what we are going to do right now. So first, let's have a look at our raw dataset. As usual, we already downloaded the data, and let's see what we have. Okay, so we see that we have data that spans the period of from 1989 to 2022. So that's more that we need. We have to subset the data to have only from 2000 to 2019. It has a latitude and a longitude that is constant because, of course, it's located only in this location. We don't have any. It's not a map with pixels with values in them. It's just one fixed location. And apparently, it has several depth levels. In this study, we'll select only one. And it has many variables because, of course, this instrument measures a lot of things besides salinity. So the first step in this process is to identify which variable in this is salinity. So in order to know that, you can refer to the user manual of the Siemens Institute Thematic Assembly Center because it describes every variable name and what it means. And as it happens, salinity is this parameter. So of course, as I said, you can either find this by looking at the user manual, or if you can also just check quickly the attributes, but with this icon, the attributes of the different variable, and see which one is actually salinity. So here, when we click on this one, we see that it is indeed practical salinity expressed in 0.001, which basically translates to gram per kilogram. So 1 in this unit basically means for 1 kilogram of water there is 1 gram of salt. Okay, so it's explained here, practical salinity unit. So let's have a look at our raw dataset. So first we've sliced it to subset it between 2000 and the end of 2019, so basically 2020. We've selected one depth level. Here it's number 3 because we didn't have any data before those levels, so it's not always well explained whether how in situ products are structured. And here we are selecting only one depth level. So we are plotting the values over time, and we can see that it has a rather astonishing profile. So the data looks quite noisy. There are holes in it, and we can't see much in here because there are outliers here that are extremely low. So those values are probably from wrong measurements, and they flatten the graph. So first, let's just zoom in on this in this frame of practical salinity unit to see better what the graphic looks like. And to do this, we'll just need to change the limits on the y-axis. So let's replot this. Okay, so now we only between 28 and 35 PSU, and we still can see that the data is noisy, and yes, there are indeed missing values from time to time. So now the next step will be to clean the data. If you look back at the dataset that we have opened before, you see that along with the practical salinity variable, there is a practical salinity QC variable, and QC stands for quality control, and it's basically a quality flag for this data. So actually, for each value of salinity, there is also a quality flag value, and this quality flag value can be from an integer from 0 to 9, and each value has a different meaning that is explained here. So they are written here. It is easier to read in this table. So you have a value 1 for good data, value 0 when no quality control is performed, 2 probably good data, and afterwards those values refer to usually bad data, except 7 and 8 which are nominal value, interpolated value, and 9 who is just a missing value. So the idea here will be to remove from this data all the data that can't be considered good. So we'll only tip that sanity values with a quality flag equal to 2 to 1. We'll also keep 7 and 8. So here is the data. Here we have performed no cleaning, but it's just to see what are the quality flag values in the data. So we can see that there is a lot of good data, a lot of missing values, and some data that have been changed. It's hard to tell, so we are probably going to remove those values. And we also have some values flagged as bad data here, which seems to correspond with the outliers we've seen before. So let's replace all those bad data with none, not a number, and see what comes out of it. So here, this is the little function I have created in order to filter out all the data that is not good. And we create a new variable in the dataset which will be called particle salinity clean. And to this variable we will apply our function, our filtering function. So this filtering takes a little time. I'm going to pause the video and come back with you when it's done. Okay, so well, it took approximately 30 seconds to 1 minute, so it wasn't that long. So our dataset is here. We have our data, and let's see what happens now when we plot the data. Okay, so we have made two plots here. This is the clean salinity data that we have filtered. And as we can see, the data is still a little bit noisy, at least from this zoom level. But for example, we can see that the very low values that were probably wrong have been removed thanks to this filtering. So it shows that it was relevant to perform this quality control. There are still missing values in this data, but in order to solve that problem, as we only need yearly values to study the trend over the past decades, we've just performed resampling to have yearly values and well, yearly means actually, and that's what we have here. And we can see that we have a slightly increasing salinity, especially from 2008. So yes, it's slightly, it follows a pattern that seems similar to the pattern followed by NPP. So we'll see in the next section when we calculate the correlation whether this is significant or not. So at this point we have computed many time series of different environmental parameters. As a reminder, we studied acidity, nutrients, so phosphates and nitrates, salinity, and sea surface temperature. And so now we want to quantitatively assess if those parameters can be drivers of the evolution of NPP in the German bight. So now we're going to actually calculate the correlation coefficients of those time series with the time series of the NPP. So this is the subject of the section number 6. So let's do a first example in detail with nitrate. So as a reminder, let's plot our two time series that we had computed before. So this is the NPP, if you can recall the shape of the curve. Its shape is much clearer because we don't have the monthly values behind that flatten the graph a little bit, but it is the exact same as the one that we've seen before. Oh, no, this is pH. Yes, so this is the yearly means of NPP, and it is indeed the same graph as here. And this is nitrate concentration. So yes, the two curves look a little bit similar. And to quantitatively assess it, we are going to calculate the correlation coefficient between the two. To do this, we're going to use the Pearson correlation coefficient, and we will calculate it thanks to the SciPy Python library. It is the most common coefficient to assess the correlation between two time series. So, what is our result? As we can see, our correlation coefficient is 0.627, which is a positive correlation. As a reminder, the closer the coefficient is to 1, the stronger the correlation is. If it's very close to -1, there is an inverse correlation. And if it is close to 0, there is probably no correlation. So this is quite strong. And more importantly, the Pearson R function also comes with a calculation of a p-value. And this assesses the statistical significance of the result. And if it is traditionally, if it is below 0.05, there is a very likely chance that the two parameters that we're looking at are actually correlated. So yes, this is a strong result, and it shows that nitrates and NPP are quite closely correlated to each other in the German bytes. So we've seen this in this example in detail, so we'll perform exactly the same thing for all the other parameters, so acidity, phosphates, nitrates, SST, and salinity. So this is a function I've defined before, but don't pay attention to it. It's not used anymore in this section. We're just computing the Pearson coefficient just like before, and we're using the pandas module very punctually just to display the results in a table. So I've executed the cell again, and in this column we have our correlation coefficient and the p-value here, which shows the statistical significance. So we have the same result as before. This is what we found before with nitrates. We still have our correlation that is quite high. We have an even higher correlation with phosphates. The correlation coefficient is very close to 1 and the p-value is very close to 0, which shows that this is a very significant result. As for temperature, well, there is little to no correlation with NPP. As we can see, it's quite close to 0, plus the p-value is high, so there is nothing significant about those correlations, and we can't draw any conclusion from this. And the same thing goes with salinity, which also doesn't enable us doesn't allow us to conclude there is a relationship with NPP. And there is pH, which is more ambiguous in this area. We have a little bit positive correlation, 0.43, with a p-value that is quite small. It's still above 0.05, but it's is very small, so perhaps in other areas we could find a stronger correlation with pH, but in the German byte it looks ambiguous. So from what we've seen, phosphate and nitrate, so the nutrients, are the two most correlated parameters with NPP, which is consistent with the fact that primary production of biomass is highly dependent on the input of nutrients in the water. So this is a consistent result, and this is something that we could have expected. And as a conclusion, we'll plot all the correlated parameters that we have identified, so phosphate, nitrates, along with NPP on the area. So here we go. Whoop. Temps mort. So as a conclusion, we are going to plot the map of the NPP trends with its most correlated parameters, nitrate and phosphate concentrations. So here we go. Okay, so as a reminder, this was our area of interest with our decreasing trend over the last 2 decades. This is our average net primary production with the monthly and yearly values. And finally, those are the two parameters that indeed, especially phosphate, we can see why the correlation was so strong. The curve follows exactly the same pattern as the one from the NPP. So yes, thank you for following this training. And if you want to exercise yourself, there are a few things that you can do. So for beginners, I would advise you to try plotting the map of NPP at another date than the one that I had chosen. For the part on the SST, sea surface temperature, as you remember, we had merged 4 different files together to have one single file. You can download more products to have a longer SST time series, so longer than just from 2000 to 2019. And yes, so in this notebook we have studied the German byte, but there were other areas where we could see some decreasing in the data of NPP. So you can try, for example, to do the same study on other areas. Here is an example on the channel. So you can try to reproduce this conclusion graph. As you could see, there was also a good correlation with the pH that we had identified, but you can also try to do the same thing on other areas, this one, for example. And finally, we have chosen a limited set of parameters to study correlations, but you can choose others such as CO2 pressure or dissolved oxygen in the water. Those could be also interesting parameters to correlate to the NPP time series in the area of your choice. So thank you for your attention. We hope that this notebook gave you plenty of tools and insights to help you manipulate ocean products with Python. And if you have any questions, don't hesitate to contact us at servicedesk.siemens at Mercator. J'ai mal dit l'adresse mail, je recommence. So if you have any questions and if you want to contact us, don't hesitate to write us at the following mail address, servicedesk.siemens at mercatorocean.eu. We'll be happy to hear from you. Thank you very much and have a good day.